Alright everyone, let's look at this probability example, and we're gonna talk about two major issues, one of the actual three. And first, law of total expectation and law of total variance and CLT, center limit theorem. And we're gonna look at what would you do if you have like two random variables, and if you're able to, let's say they are discrete for the argument, and if you're able to, let's say, represent them as, okay, x is 1 for probability 0.1 and x is 2 for probability, let's say, 0.9, and same data set you have for y, and you need to convolve them, and you need to use MATLAB. I mean, you can use MATLAB for that will be easy. And another issue, let's say you have an IID random variables and it's discrete, let's say, or you can represent it as that such. So you also have, let's say, S100, right? So you basically sum 100 of them, and this has something to do with CLT, and we will look at how would we generate the PMF, since this is discrete, PMF of such a mathematical object. Alright, so this is a nice example. We will talk a couple of, deep, like fundamental issues. Okay, and I think this is my first probability related video. Alright, it's been some time, okay, since I, produce a video. Alright, in a casino, what you play is determined by a coin flip, and this fair coin, so it's directly that it's 50%, 50%, right? So there are two games, chess and poker. For some reason, this is that type of casino, and it says that when you play chess, okay, these are your priorities, and when you play poker, these are your priorities, right? And part A, for each round of game, what is the mean and variance of the game? Okay, so first of all, we have two main random variables. First random variable is, let's call it game, right? And usually you would expect your first instinct is to write it as, okay, this is a random variable and this should be 1 with the priority, let's say 0.4, and this should be also 2 with priority 0.6, something like that. But these are numbers, right? And it can also very well be like some type of construct, right? So this is one of those cases. So game, the random variable, can be A, like to represent the game A, and let's say game A is chess. Actually, that's what I did. Okay, this represents chess for this problem, and B represents poker, right? So okay, first random variable is game, right? And it takes two values. A, it can be A with the priority half, and it can be B with priority half. Okay, so other random variable is that gain. However, it is stated in the problem such a way that the problem doesn't say, okay, gain takes this value with the probability xyz. It doesn't say that way, but it states or explains that indirectly, right? Gain given, we know that it is game A. Okay, this random variable, we can write it that way. We know it like completely, okay? And we know how to represent it. Okay, so our gain given it's game A is this, and where did we get that? From the problem. Okay, and the same we can do for gain given it's game B. We can write it that way from, again, using the information given in the problem. All right, so just for completeness, and we can write gain in such a way that, right, I will not explain why. I mean, it's kind of obvious actually. Okay, So there's 50% chances, okay, and then you basically multiply every probability with 50%. Right, first you need a coin flip, 50%, 50%, and then A, and then game A, and then game B, and you know what their values and probabilities are. Again, the same thing for game B. I mean, you may think that, okay, it was 50%. Okay, let's say maybe it was 60% or 40%. So what I'm saying is that it has nothing to do with the value is at, and it's a general concept. You can, imply that to other problems. Okay, easy. And we will not use this for stage A and stage B but for simulation we will use this. And yeah, we will have some type of simulation, MATLAB simulation. MATLAB is really good for those type of applications. All right, so let's move on. Before moving on, is like we are asked about mean and variance. Okay, mean and variance of gain, right? Gain. Okay, so part A, let's find mean, and for that we're going to use law of total expectation. And this is basically the general expression of law of total expectation. And so for this specific problem, right, this is our gain and this is our game. All right, so basically we can write it that way. Gain, given that is, like, gain depends on game, which game we play, right? And gain, expectation of gain, given it's game A, right? So what we need to do is we are just going to look at here and then find the mean. How do you find the mean? This is value, this is probability, right? You just multiply them and then sum them up, which is 0. Okay. The same for, and also don't forget the probability of you playing game A, right? And same steps you apply for game B, and it is 0. All right, we are done with expectation of gain. And variance will not be that easy. Variance going to be kind of complicated, and law of total variance is very important, and I think it may have the potential to make some problems, not all problems by the way, but some problems quite easy, right, and quite straightforward. So this is the general expression of law of total variance. And for this specific problem, okay, this is the equation that we're going to use. And so there are bunch of small steps that we need to take before computing this directly. So first talk about this and that expression. So before saying more, I wanna state, let's say this expectation, we have two random variables x and y, right? Y given x, expectation of y given x. This is your first, if you're not familiar with law of total expectation or law of total variance, your first instinct when you see that might be, okay, this should be number. Actually no. And I mean, this is actually a function of a random variable x. This is actually function of x. So it is okay, this is like a system you made, or function basically, and you give me an x, and I'm gonna give you, like, using that x, I'm gonna give you a number, right? So this is when you give me the value of x, I'm gonna give you a value, right? But I'm not writing it that way, I'm writing this way. So I didn't give you the number. I want you to basically give me the function mapping from x to this, right? I hope I didn't make it more confusing. All right, so anyway, one more time, let's say we have x and y, they are random variables, and expectation of y given x is a random variable. Alright. Another thing, variance of y given x is also another random variable. Again, it's also a function of x. Like this expression is a function of x. Alright. So let's move on. And since it is a random variable, expectation of y given x, we can find what can we find? We can find its mean and we can find its variance. And if you're really crazy, you can find its like you can compute its third, fourth, center or non-center and moments. All right. So first, let's try to find this expression. And yeah, like I said, this is random variable and this is the function of that random variable. Right? Again, the same stuff for variance. And it's been some time that I produce any video, so I still try to remember how to use this tablet. All right, so this is the random variable. So this is the function of game, right? And we know game from the problem. Game take two values. We have game A and game B, right? And each with probability 0.5. Okay, so basically we're gonna write it that way, right? When we write it that way, this is a value now, right? Because we know the value of the game. So we can compute this, and same goes for this expression. And since they are 50% possibilities they have, and we can write it that way explicitly, and then we need to compute that. And from the previous step, when we were trying to find the mean, and we know that they take the value 0, so at the end this is 0 with probability 1. So what does it mean? It means it's not even random, it's just the deterministic number which takes on the value 0. All right, so let's move on. And yeah, so this is deterministic number, right? What does it mean? And we want to, okay, just let's look at this, right? Here we want to compute what? We want to compute variance of this expression. And since this is not even random, this is deterministic, meaning it has no variance, hence variance is of that expression is 0. So we write it that way. Okay, so let's continue, and we will need to talk about law of total variance. And now we need to talk about this expression. Like, we are going to use the same idea, right? This expression is a function of game, and game has two values, A and B, right? We're going to write it that way. And when we express it that way, it is not a random variable now, it is just a value, right? It's a number. And we know that game takes on the value game A with the probability 0.5, and hence we write it that way. So what we need to do is to compute these two expressions, right? So gain given A, but before doing anything, let's remember this expression. This is a random variable, right? Okay, this is a random variable, and when you compute its variance, it's a value, so don't confuse that. And this is a random variable. Let's express it explicitly. Okay, I mean, we actually written like here, right? So I'm just repeating for clarity. And we need to compute it is square. Why? Because whenever you find yourself trying to compute variance, right, like best thing to, or easiest way to keep in mind is that, okay, the second moment equals variance plus square of mean, right, of the random variable that you're deriving with. So I find it for some reason easy to remember, and because of that, and also it makes things easier, right? Actually, for discrete, like here this is binomial, but I'm sorry, Bernoulli, but for multinomial distributions, it is quite easy to compute that, right? It may look scary at first, but if you have like multinomial distribution, and it's easy. So you just need to square the values, right? That's it. That's all you have to do, and then express it that way. So I mean, there is no reason for us to write it that way, so let's write it. And as this takes on the value 1, and with the product of 1, again, this expression is not even random at this point. This is, I mean, its variance is 0 basically. Okay, and but we're not gonna use this variance. Yeah, this is that expression, right? We're gonna use it here. Okay, so this is, and its expectation is 1, right? Here we write it that way, and we know that expectation of gain, given that it's game A, it was 0, and 0 squared is 0, all right? So at the end, variance of gain given game A is 1. Okay, so let's continue. Let's do the same thing for B. Okay, here let's express the gain given game B. This is a random variable, and these are the values, and these are the probabilities. So this is a multinomial distribution. Alright, so we need to square it, and you just need to square the values, right? And if you, I expressed it written that way, by the way. And so you just step by step do that, and then when you have the same values, you basically, like, there's no reason for you to write it in different entries, and you can basically collapse them, and that's it. This is the random variables, this, right, random variable expression. And what do we need? Yeah, we need to compute this mean, right? Basically you need to multiply them, and this is 3 times 2 is 6, and this is 0. So mean of this expression is 6. Here this is 6, and we know that from the previous stage of the problem it was 0, and we have 6. This is the expression, so we're going to use these two expressions, and that was the problematic variable that we needed to compute, and we write it explicitly that way, right? So this is 1 here, and this is 6 here, and with the probabilities. So we need to compute this mean, right? Basically you need to multiply it, 0.5, this is 3, sum them up, 3.5. okay, here. So at this stage, finally we know we have the random variable gain, and its expectation is 0, mean is 0, and its variance is 3.5. If you say that, or if you're thinking, I mean, it was very easy to explicitly write the expression for gain random variables, and it is easy to compute the mean and also variance just by looking at this table, right? So why did we do all of them? It may not be perfectly, clear why we use law of total variance for this problem, but there are some problems, they're quite intricate, and law of total variance makes it easier. My general purpose for this example is to explain the law of total variance, how to apply it, and you may think that it's kind of complicated, but there will be a similar problem, and law of total variance might make things easier, right? For example, in a way this was like a small scale problem, so you would be able to write it that way, right? And because of that, like this, like I said, there is a fine balance between having a problem that's easy, and also having a problem that's easy to show the steps when we use law of total variance, And also, like, there's another balance, is like you don't want to make it too hard, so it would be hard to understand the steps when you want to use some algorithm, right? So that's it. You try to be here at that stage. And right, part B of this problem is that what is the probability that you win over $10 after 100 games, and use central limit theorem. Right. Okay, so this is the expression that we need to compute, and we can write it that way. And expression for S100 is this, right? And here, the reason why we computed mean and variance, now it will be obvious, right? I mean, you can, like, just for the fun of it, you can also, compute it. That's right. And let's look at it. So we need to write this. So for the center limit theorem, basically, when you have a multinomial distribution and you have IID, like multinomial distribution, and you sum, I don't know, capital N of them, what you would end up with is S capital N. And the idea is that you can find, if you can compute this mean and variance, basically it would be like a continuous variable, and it would make things quite easy for you, right? Now we're gonna see. And if you think about it, this is not an easy problem unless you are using MATLAB for that. And we will also talk about this, like how to, let's say you don't know about anything about like center limit theorem, but you know how to use CONV function of MATLAB, like convolution, right? Why? Another quick thing to say, note that why would you use convolution when you have X and you can, it's a multinomial distribution, and let me write it, multinomial distribution, right? And or maybe Bernoulli, okay? And you know this and you know that, right? And when you sum them up, you basically, let's say it is PMF and this is its PDF. You just convolve them, and let's say this is Z. So Z is this. By the way, I'm not even sure, right, if that's the shape would make sense, but we are convolving the two given PMFs to find the resulting PMF of the resulting random variables PMF, basically. Okay, so that was a long detour. So what we are trying to say is that CLT, center limit theorem, makes things quite easy, right? And now we're gonna see why and how. Okay, first though, we need to compute mean and variance, right? So what we wanna do is to represent this is normal distribution, and for that we need to find the mean and variance. So let's compute mean, right? Here, like step by step, I'm trying to show the steps. And okay, we know that it's IID, like in the problem, right? It's stated IID, and indirectly maybe, so we can pull in, and we know expectation of the gain, like in the first stage, exit part A, we computed that and it was 0. And so okay, the expectation of our S100 variable is 0. Okay, so variance, right? Again, we can write that way, and we can put it here because it's IID, right? Okay, so we know what the variance is, 3.5, and then times 100, we have 350. So we now can write S100 as a normal distribution with, since we know it's mean and variance, and this is the expression. All right, using this approximation, we want to compute this, right? So whenever you have that, right, and if it is not like this type of, it is in this form, like 0 mean unit variance, right, and you need to normal, quote unquote normalize it. How would you do that? Like, this is an inequality, right? So you basically subtract the mean from both sides, and then divide it by its standard variance, standard deviation, or square root of its variance, right? And what you end up with is this expression, which is zero mean unit variance, and it is like sometimes they write it as z, right? So when you have this expression, and this, if that random variable is zero mean unit variance, and by the way, be careful about the directions of the inequalities that you have, and if you know this value, you can express it that way, right? This is a phi function, or on top of that, look, I may not be sure about this, but yeah, I need to check that actually, but I'm gonna say it anyway. So if you want to be really annoying about this, you can also write as q, right? 10 over 350 square root of it, because for some reason it makes sense for people to write, instead of writing 1 minus phi of x, they decided to come up with a new variable, a q function. So that's it. And for phi function, by the way, there is no phi function like directly in MATLAB, and they use error function, they call it, and this is how you, like, as an enormous function or something, you can define it that way, and then put this value here, and MATLAB would give 0.3, which is the probability. So let's continue, and we will see 3 simulations, and basically this is MATLAB's way of, or this is like in a way Monte Carlo way of generating that. What we are trying to generate is that, and what you end up with when you have 100 games played and you wanna plot its PMF of what? PMF of gain, right? And this is basically what you would do, and because of that you would need to have samples, like we chose like 100,000 of them, and then since we have 100 games, right, and we allocate memory, number of samples, and we know the probabilities and values, right, and run sample is a quite nice and suitable function for MATLAB function for that, and I will not even explain it, and after that you just plot the histogram. That's it, right? And this is your result, right? As you can see, like we were right for we basically model this S100 random variable is a Gaussian, and you can see that's why that was the case, right? Okay, so another issue, for example, that bothered me, and when I was learning that, you may think that, but it is, wait a sec, we have some discrete values and some discrete properties, and we convolve them, so we have like finite, let's say 600 or something points. But I mean, isn't Gaussian random variable should go to like infinity? The answer is yes, but after a while it goes to almost 0. So like I said, this is approximation, this is not exact value, but it is quite good approximation, right? And another thing, it makes life easier, and you would like that. So let's look at the code, and if you wanna compute, like for example, that, by the way, this was not even approximation, this was just like Monte Carlo, right? So this was the worst thing that you can do, like, so random sample is MATLAB function, but and you don't need random sample function, and you can have just with using runs function of MATLAB, and you can generate that result, so you wouldn't need any probability basically, right? Okay, but you would need to have RAND, right, rounds. So to be honest with you, I don't know how would you like generate random. It's not a simple task, I think. Okay, but when you have round, okay, this is another subject, but when you have round, so basically when you have like a when you are capable of generating or sampling from a distribution which is like uniform between 0 and 1, you can, there are ways to generate other random variables like Gaussian and Poisson, something like that. Okay, so this is phi function, right? So these are the properties. Actually, I first written that way, and then I realized that -3, -1, 0, 1, 3, right? But we have -2, like, so okay, we don't have that, but let's write it and write the probability as 0, right? To make things easier, because we will need to convolve that function like with itself, basically like 100 times, right? And actually 99 times. So okay, so basically this is what you do. We just convolve it, right? We just convolve it, and that's it basically. And it basically comes from the following: when you have two random variables, right? And when you have, like, by the way, they can be continuous too, exactly. So these, like, they can be PDFs, right? So is a convolution is not like a discrete concept that you would only compute for discrete datasets. Like, you can also do that for like continuous functions. All right. So when you have x plus y, and when you have the random variable z, and to find its PDF or PMF, you would convolve them. That's it. But when it's discrete, it is easier, right? Okay, it's something that MATLAB can handle it. And so we also know that -3 and 3 are the maximum values, and we play like 100 times, and at the end of our basically graph, we will have -300, and it writes 300. So it will be between 300 and -300, and it will be integers, right? We don't have any rational numbers here, so like all of them would be rational, and sorry, integer numbers, right? And all of them are integer, and we're gonna convolve them, so what we will end up with will be integers. So okay, and we also know the minimum and maximum, and also minimum and maximum, and we also know the number of plays we have. It was 100 for this problem, so we can generate the x-axis by defining like integers, basically. Okay, and because this can be annoying for other types of problems, and it may be something that you need to, be careful about. And that's it. That's basically, it looks quite, this is correct, by the way. This is like, this is not approximation, this is the true PMF of S100, right? So okay, and I mean, I also plot the Monte Carlo one, and they like 100 all quite match. Okay, so let's move on to another thing. And this part is the same. This part is the Gaussian approximation, right? So we know the mu, we know the like mean of S100, and we know the variance of S100, and we basically, as an anonymous function, write the PDF of Gaussian approximation. And okay, it takes the value x, and give me the x, and I'm going to give you the, using mu and sigma, I'm going to give you the probability that this random value can take on. And this just the typical PDF of Gaussian random variable, right? Okay, that's it. I didn't need to write that actually, but anyway. So yes, for x values, and we know that from -300 to 300, why? because the maximum profit we could get was 3 and minimum was -3, and we had 100 games, so maximum at the end of that, I mean, it would be almost impossible, but maximum you would get and minimum you would get are -300 and -300 respectively. So that's it. We also wanted to compute Gaussian values, probabilities using Gaussian approximation to see how well the Gaussian approximation would be, I mean, would fit for this problem, right? And okay, for 601 points we are computing is probability, right? And we can see real PDF and Gaussian approximation, they quite match, and that's it. I think that's over. Okay, thank you, and don't forget to subscribe, and happy Thanksgiving.